Two lens systems. Many optical instruments use a number of lenses together. The easiest example is a two-lens system. The main advantage of using a two-lens system is to get more magnified images than a single lens can produce. The most common use of a two-lens system is a microscope and a telescope. Both use two converging lenses. Let's look at a two-lens system. In orange right here, we have our object. Here we have the first lens, f1, which is converging. Over here we have our second lens, f2, which is converging. Now, light from the object is going to go through the first lens and it's going to produce an image over here. The object now is going to produce an image using lens 1. So in red here I have my ray number 1, blue ray number 2, they cross, they produce. So in order to avoid too much stuff on the screen, I'm not going to follow through with the rays here. So I could see that the object has S1 because it's associated with the first lens. Then I have image S1 prime, which is associated with the lens. Now, this image of lens 1 now becomes the object of lens 2. So this image is now a distance S2 in front of lens 2, and this will now produce an image through lens 2. So drawing out the ray number 1 in orange and ray number 2 in green, where these rays cross, I now have image 2. This object, the image of lens 1, is labeled S2. This image is labeled S2 prime. One key piece of information that is typically given in a two-lens system is the distance between the two lenses. And this distance is labeled D, the distance between the two lenses. If we look at the characteristics of image 2 here, you could see that it's on the other side of lens 2, on the right. Therefore, it's a real image. If I compare this to the object, you could see that this image is erect. It's smaller in this case, and therefore it's real. Simple microscope model. Although real microscopes are more complicated than what I'm suggesting here, we can get a feel for how we can get, a larger magnification for this model. The first lens has a long focal point, whereas the second lens has a short focal length. The main idea is this. You want to place the object between 2f1 and f1, because then it's going to produce an image that's magnified. But if I now take this image of lens 1, and it's now the object 2, if I place this object inside the focal point of f2, there's a second magnification that goes on. In other words, the object is magnified by both lenses such that the total magnification will then equal the magnification of lens 1 times the magnification of lens 2. Let's draw this ray diagram in steps. For a microscope, we start with a small object. We place that object between 2f and f. Now, drawing ray 1 and ray 2, I get an image here in pink that should be outside of 2f. This image now becomes the object for lens 2. We want to put the focal point of lens 2 such that this guy just falls inside of focal length f1. Let's draw that in. So now that I have the image of lens 1, now I'm going to draw ray number 1 in orange and ray number 2 in green. And when I follow them back, I now have this image produced by both lenses. So what you could see here is that if I start from the object again, it starts off at about half a square. When I get to the image produced by lens 1, you could see that it's bigger than 1 square. So now this image is the object for lens 2, and you could see that it gets magnified again. So there's 2 magnifications. That's what a microscope effectively does. Simple telescope model. Telescopes, like microscopes, are more complicated than what I'm actually showing right here. But let's imagine the following thing. Stars are far away, so I imagine that they're big, but when we look at them as telescopes, we know that they're going to produce images very, very, very close to the focal point. So you could see F1 here has these black F and 2F points, whereas F2 has these baby blue focal points here. So this image that's really far away is going to be very, very, very close to the focal point. So what we want here is that we want to put the focal length of mirror 2 to be very, very close to this so that it has maximum magnification. Let's do that with the ray diagram. So the image from a far object is then going to be very close to the focal point, as expected. The image of 1 is now the object for lens 2, so let's do that. So I'm going to draw my ray number 1, which is in orange. I follow it back, then it goes through the focal point, through the middle of the lens for ray 2, and as these rays cross, they're back here, and you could see that this image is larger than what that is. So once again, by placing the image of the first lens close to the focal point of the second lens really magnifies the image. So let's look at some things conceptually. The difference between a 1 lens versus a 2 lens system is that we always know how a 1 lens system is going to behave. For example, if I have a real image, that can only be produced by a converging lens, and that thing is inverted. While if I have an erect image, it's always going to be virtual, and that could be produced by either a converging or diverging lens. But when you get to a 2 lens system, this erect versus this inverted is more complicated now, because I could have images that are erect that are real. Here's an example here. So I'm going to start off with an object that's outside of 2F. So if I look at ray 1 and ray 2, it produces an image right here. Now if this guy is outside of 2F for the second lens, you could see that ray 1 and ray 2 are then going to form an inverted image of this image right here, which is now the object of lens 2. And all of a sudden you see here that I have an erect image. But for a 1 lens system, we always knew that an erect image was virtual. That's not true for a 2 lens system. The fact that this image here is on the right side of lens 2 means that it's real. In this case, it's small and erect too, but I have a real image. So one has to be careful about, defining when an image is real or virtual. So in summary, for a 2 lens system, images can be either erect or inverted. What determines whether an image is real is if the final image is to the right of lens 2. If it's to the left, it's virtual. Last thing we need to talk about is virtual objects. Real objects always occur for a single lens. For a 2 lens system, however, there are both real and virtual objects. A virtual object is when an image from lens 1 lands on the other side of lens 2. So when I look at this object and I look at lens 1, it produces an image on the right side of lens 2 here. So to separate lens 1 and lens 2, I have the focal point of this diverging lens in purple right here, or violet. Now, because it's on the other side, I would mathematically write S2 as a negative value. Now let's draw the ray diagram for this because it's exactly the same. Virtual objects and real objects have the same thinking of ray diagrams. So now with my pink virtual object, I'd start the same thing now. Ray 1 goes parallel, then goes through the focal point, and then I follow it into the right side of lens 2. The ray number 2 starts at the tip, goes through the focal point, and so therefore ray 1 and ray 2 cross, and I get this violet image that's inverted. It's going to be smaller than the original object, but it's going to be real because it's on the right side of lens 2. Let's do our next example, 34.3. A sand grain is 3 centimeters from thin lens 1. The distance between focal point and lens is 4 centimeters for both lenses. The lenses are separated by 8 centimeters. What is the final image location from lens 2, the image characteristics, and draw a ray diagram for the situation? Start by drawing an accurate diagram for the situation. Lens 1 with focal length of 4 centimeters is right here, and the scale is that 1 square is equal to 2 centimeters, so 2 squares gives me 4, and then I got my 2f at 8. The separation between the two lenses, where this is f2 right here, is 8 centimeters. So if they're separated by 8 centimeters, then the focal length of f2 is exactly at the same spot as f1. So f1 and f2 are at the same locations. Let's draw the rays for the first lens. So for this object, I have my ray 1, ray 2, they cross, there's my image. So this image is now the object for lens 2. Now to draw the image for the second lens. So the final image is where these two rays cross. Conclusions from the ray diagram. This location right here is the final image location, and using the scaling of 2 centimeters per square, then that gives me 2 plus 1 roughly. I'm going to have a negative 3 centimeter. Since this is on the left side of the lens, the image is virtual, and we could see that it's erect and it's smaller. So if I compare the magnification of for this image here, I compare that height to that height, and you could see that it's roughly about half. The fact that it's plus means that it's erect. So let's go do the calculations now. The ray diagram, lens 1 has a focal point of 4 centimeters and an object distance of 3 centimeters. So that's inside the focal point, so we expect a virtual image. So the thin lens equation says then S prime is then going to be S1 times F1, S1 minus F1, which then gives me minus 12 centimeters for S1 prime. From the magnification equation, we could see that M1 is plus 3. Now if we go back to the ray diagram, let's see if that's true. If I look at my object, you could see that the image is 3 times bigger. So it looks like those numbers are turning out pretty good. The image 1 becomes object 2 for lens 2. So we got to figure out the distance between image 1 to lens 2 here. We do that by going back to the ray diagram. So I need the distance from image, this pink image, all the way to lens 2. I know that the difference between the two lenses is 8 centimeters, and I know the distance from lens 1 to image 1 is minus 12, so therefore that distance is then going to be 12 plus 8, and that becomes the object for the second lens. Creating this picture, the distance from the pink image 1 to lens 2 then is this going to be this 12 plus this 8, so therefore the object S2 is in the sum of these two, which is 20 centimeters. Calculate mathematically the second image and its total magnification. Lens 2 calculations show the following. With a focal point of minus 4, an object distance of 20 centimeters, the thin lens equation tells us that the image S2 prime is at minus 3.33 centimeters. It's to the left of the lens. So of course we knew that that was going to be virtual. When I calculate the magnification for M2, we get 1/6. So the total magnification is that it is plus 2/3. The image characteristics are as follows: smaller and virtual.